You look up and see blue, a smooth, generous wash above the city, as if the world were painted with a single calm brush stroke. You look farther up, though, past the blue, and space is not blue at all. It is black, a deep absence that swallows stars between pinpricks. Two neighboring vistas, two utterly different colors. Why does the air turn light into color, while the emptiness beyond becomes an absence of color? What is the hidden tension between matter, light, and the machinery of human perception that makes one a color and the other a void? The physics that explains the sky's color was formalized in the 19th century. John William Strutt, Lord Rayleigh, showed that when light encounters particles much smaller than its wavelength, the amount of scattered light depends strongly on wavelength. Shorter wavelengths are scattered far more than longer ones. Rayleigh, 1871. This mathematical insight turned an old observation, that scattered light looks bluish, into a quantitative law of nature. Rayleigh, 1871. Later work framed the full range of scattering processes, from Rayleigh's dipole limit to the more complex Mie scattering that governs clouds and aerosols, Bohren and Huffman, 1983. That is the physical backbone. The air's molecules scatter sunlight in a wavelength-dependent way, while larger particles scatter differently. But a complete explanation must couple physics with biology and history, with the shape of sunlight, the filtering by ozone and molecules, and the human eye's response curve. Bohren and Huffman, 1983, Palmer, 1999. The human system. Color is not an intrinsic property of light that simply sits there. Color is an interpretation, the brain's answer to patterns of wavelengths arriving at the retina. Sunlight contains all visible wavelengths, but the eye does not register each wavelength equally. Human photoreceptors, cones, have differing sensitivities, and the brain fuses those signals into a single percept called blue. Palmer, 1999. Two facts matter here. First, Rayleigh scattering preferentially sends short wavelengths, blue and violet, into directions away from the sun, so the overhead sky is dominated by short wavelength light. Rayleigh, 1871, Bohren and Huffman, 1983. Second, our photopic vision is tuned so that the spectral band we call blue produces the strongest, most salient signal under daylight conditions. Violet contributes, but the combined effect of solar emission, atmospheric absorption, and receptor sensitivity makes the sky register as blue, not violet. Palmer, 1999, no AA explanation, ND. Put differently, the sky's blueness is a three-way conversation: sunlight spectrum, the atmosphere's wavelength-dependent scattering, and the eye's filters and neural machinery all agree on blue as the resultant message. The pressure, physical constraints that create the difference. There are three limiting conditions: density, coherence, and illumination geometry, that determine whether a volume of space will appear colored or black. Density. Earth's atmosphere, though thin compared with solids, contains enough molecules per cubic meter to scatter a measurable fraction of sunlight. Each molecule acts like a tiny dipole re-radiating light. Collectively, they produce the diffuse illumination we see from everywhere but the sun's direction. Rayleigh, 1871, Bohren and Huffman, 1983. Coherence, or its absence. Scattering by many independent tiny emitters produces diffuse, incoherent light. It washes the sky with a broad, soft color. In contrast, empty space lacks scatterers. Without something to redirect sunlight into your line of sight, there is nothing to transform a beam of sunlight into a diffuse field. You either see the direct sun or you see dark. NASA Star Child, ND, New Horizons Observations, 2021. Illumination geometry. On Earth, you stand inside a light-filled bath. Most lines of sight intersect scattered light. In space, most lines of sight do not. They point into vacuum where photons travel straight and mostly miss your eye unless a bright source sits along that line. The result is a sharp contrast, bright suns and black void between them. NASA 2021, Scientific American, 1999. Most likely, modest atmospheric change, same basic physics. Earth's atmosphere will continue to scatter sunlight in roughly the same way for the foreseeable future because Rayleigh scattering depends on molecular composition and density, which change slowly on planetary timescales. Short-term variations, aerosols from volcanism, pollution, or wildfire smoke, will modify the sky's hue and brightness locally and temporarily. More aerosols shift scattering into the Mie regime, muting blue and increasing whiteness, or reddening at sunrise and sunset. Human-driven changes will produce regional alterations, paler skies where particulates rise, deeper blues where air clears, but the core physical mechanism that turns molecular scattering into blue will remain intact. Observers and instruments will still classify the sky on the same physical basis, though the precise tint and contrast will vary with local conditions and seasonality. Transformative, less likely. Persistent global aerosol loading alters perceived sky globally. If atmospheric aerosol loading became globally persistent, for example due to sustained volcanic activity or long-term industrial particulates, the dominant scattering mechanism in the lower atmosphere could shift sufficiently toward Mie scattering that the uniform, deep blue wash becomes rarer. Instead, we would live under paler, more diffuse skies, with more frequent whitening and enhanced red sunsets. Human vision and cultural descriptions of sky blue would adapt. Artists and language might shift toward different color metaphors. Instruments would record altered scattering spectra, and climate models would need to account for radiative effects on Earth's energy balance. This scenario is physically plausible and has occurred episodically in Earth's history. The probability of a permanent global shift depends on both natural forcing and human policy choices about emissions. Risk stress test. Localized extreme vacuum altitude experiences change the rule. Low probability but instructive. At extreme altitudes, in the stratosphere, aboard high-altitude aircraft or on the moon, the sky already approaches black because the column of scattering molecules above you is greatly reduced. If human activity pushes sustained long-duration habitats into near-vacuum environments, space stations, lunar bases, the everyday visual environment will move from blue interior to black exterior. That matters psychologically. Humans evolved under an atmospheric envelope that provides diffuse daylight. Living routinely with a sky as void may change circadian cues, orientation, and symbolic frameworks. Technically, nothing mystical happens. Photon transport and scattering laws hold. But the human-system interaction changes, and with it our sensory expectations and cultural metaphors. Experts suggest that this kind of perceptual regime shift could matter for design and adaptation if off-world living becomes a long-term norm. NASA Observations, Palmer, 1999. Adaptation patterns, how humans and systems respond. Biology adapts locally and quickly. The visual system adjusts its sensitivity depending on illumination, dark and light adaptation, tuning receptors and neural gain so that perceived color remains useful across conditions. Palmer, 1999. Culturally, people learn to name and interpret sky colors according to local climates. Clear, high-altitude air gives deep, nearly purplish blue overhead. Humid or polluted skies are washed and pale. Language and art encode these differences, making sky blue a context-dependent idea rather than a universal constant. Technically, we respond with instruments. Spectrophotometers and satellite sensors measure scattering spectra directly. Radiative transfer models translate those spectra into energy budgets and climate feedbacks. Design-wise, architects and lighting engineers use an understanding of diffuse skylight to shape indoor illumination that feels natural. Finally, when humans leave the atmosphere, even for short periods, designers must recreate the diffuse cues we use for orientation, temporal regulation, and emotional comfort. That is partly physiological, light exposure for circadian health, and partly symbolic. The sky is blue because matter, the molecules of air, takes white sunlight and redistributes its shorter wavelengths in all directions, while space is black because there is almost no matter to do that redistributing. But that sentence is a shorthand. The full answer is an interlocking tripod of physics, spectral content, and perception. Look at it another way. Color is a message. The sky's blue is not a property merely of light or merely of air, but a negotiated signal that arrives at an observer shaped by scattering laws and the observer's sensory machinery. The blackness of space is not an absence of light sources. It is the absence of the intermediary that transforms directional beams into diffuse fields your eye recognizes as color.